Picture this. You're a pharmacist, or maybe a quality control scientist, and you're holding a tiny glass vial. Inside is a perfectly clear liquid. I mean, it looks exactly like water. But this liquid is actually a powerful pharmaceutical drug. So how do you guarantee, with absolute certainty, that this clear liquid is perfectly pure, safe, and exactly what it claims to be? You obviously can't just taste it, and if you destroy the sample to test it, well, you've just ruined the very medicine you're trying to save. Welcome to the Day's Explainer, where we are going to solve this exact physical chemistry mystery and uncover why just one specific instrument is often all it takes to instantly check a drug's purity.
Okay, let's dive into this. Here is our roadmap for today. Number 1, the quest for purity. 2, one instrument, the refractometer. 3, polarimeters and twisting light. 4, dielectric constants and capacitors. 5, molecular tug-of-war, dipole moments. And finally, 6, splitting up, dissociation constants.
Starting with Section 1, the quest for purity, why physical properties actually matter.
So studying a drug's physical properties is basically the absolute prerequisite before you can even think about making a product. But it leads us right back to that high-stakes problem. If you have a clear liquid drug, how do you instantly know it's safe? As we said, you can't just eyeball it, and taste testing is definitely off the table. If you use destructive chemical assays, you ruin the very batch you need to sell or administer to a patient. We desperately need a way to get an invisible, instant peek inside.
Which brings us to Section 2, one instrument, the refractometer, the absolute hero of quality control.
To grasp how this instrument works, we just need to look at a classic analogy. You've definitely seen a pencil sitting in a glass of water, right? How it appears to kind of bend or break right at the surface? Well, that is refraction. When light passes from one medium, like air, into another, like water, it bends. The extent of this bending is measured by something called the refractive index. Based on Snell's law, it's essentially a ratio of the speed of light in a vacuum compared to its speed in that specific medium. It's kind of mind-blowing when you realize refraction is essentially a sudden change in the cosmic speed limit for light.
And this brilliantly illustrates why this matters so much for testing drugs. Look at the extremes we're dealing with here. Air barely slows light down at all. It's got an index of 1.0003. Water sits at 1.33, while a superdense diamond bends light severely with an index of 2.42. And actually, fun fact, that extreme bending is exactly why diamonds sparkle so intensely. Because this index is so deeply tied to a substance's core density and composition, every single chemical compound has its own unique optical fingerpart. If your liquid drug is supposed to have a refractive index of 1.50, but it measures at 1.44, boom, you instantly know it's contaminated.
So how do we actually read this fingerprint? Enter Abbe's refractometer. Invented way back in the late 19th century, this elegant piece of history is incredibly still the bedrock of modern pharmaceutical quality control. It is the one specific laboratory instrument used to measure how light propagates through liquids and solids to check their absolute purity.
The way this device captures that measurement is just brilliant. You place a tiny, tiny drop of the liquid between two prisms. As light passes through, the refractometer doesn't just look at the bend. It actually looks for the critical angle of total internal reflection. When you look through the eyepiece, you'll see a really distinct boundary between a bright, illuminated field and a dark field. By aligning that boundary with a crosshair, you can read the exact refractive index directly off the scale. It's that simple.
And this is exactly why this one single instrument is a total game changer. Because a liquid's refractive index acts as an unforgeable, holistic fingerprint. You don't need some massive laboratory running complex, messy chemical tests. Just one ABI refractometer gives you an instant, direct reading using literally a single drop of liquid. And the best part, it doesn't destroy the sample. One instrument is all it takes to act as the ultimate frontline safeguard.
Let's move to Section 3, polarimeters and twisting light, another optical detective.
Now, while the refractometer is our primary hero, light has a few other ways of interacting with molecular structures. Normal light from, say, a light bulb vibrates in all directions. It's unpolarized. But if you pass it through a special filter, it becomes plane polarized, meaning its oscillations are confined to just a single flat plane. Certain molecules, called chiral substances, have this amazing physical property. When this flat plane of light passes through them, the molecules actually grab the light and twist it, rotating the plane either clockwise or counterclockwise.
We measure this twisting effect using a polarimeter. The polarized light travels down a tube containing our drug sample. If the drug is optically active, the light rotates. At the other end, an analyzer is turned until the light is completely blocked or reaches uniform brightness.
The exact angle the light was twisted tells us instantly if we have the right active ingredients. Think about it. If a drug is supposed to twist light 90 degrees clockwise, but it twists it counterclockwise, you have the wrong molecule entirely, even if it looks utterly identical to the naked eye.
Section 4. Dielectric constants and capacitors. Invisible electric safeguards.
Because optical tests aren't the only non-destructive tricks we have, we also look at how molecules respond to electric fields. This brings us to the dielectric constant. Imagine placing a drug sample between two electrically charged platinum plates in a parallel plate capacitor. The dielectric constant measures how well that material stores electrical energy compared to a complete vacuum. A higher constant means it stores more energy by becoming polarized. Why do we care about this? Well, this property is absolutely crucial for solvent selection. If a pharmacologist needs to dissolve a drug to make an injectable liquid, knowing the dielectric constant dictates exactly which solvent is going to work safely and effectively inside the human body.
Which flows right into Section 5, molecular tug-of-war, dipole moments. This is what happens when atoms just don't share equally.
Let's drill down even further into this electrical behavior and look at the dipole moment. Take a hydrochloric acid or HCl molecule, for example. The atoms here are technically sharing electrons, but they definitely aren't sharing them equally. It's a literal molecular tug-of-war. The chlorine atom is more electronegative, so it pulls the bonding electrons closer to itself. This creates a partial negative charge on the chlorine side and a partial positive charge on the hydrogen side. This separation of charge is what we call an electric dipole. Measuring this dipole moment gives us deep insights into the actual structural arrangement and behavior of the drug molecule.
Section 6. Splitting up. Dissociation constants. How chemicals break apart.
All right, so what actually happens once that pure drug gets inside your body? Represented often as Ka, the dissociation constant is basically the ratio of broken apart ions to the intact molecule. Now, don't let the formula intimidate you. This isn't just arbitrary math. It's a vital metric for understanding the strength of an acid or a base when it hits water.
So the crucial point for us is this comparison. A strong acid has a really large Ka because it breaks apart almost completely, just flooding the solution with ions. A weak acid, on the other hand, has a small Ka because it only partially breaks apart. Knowing this exact Ka value tells a pharmacologist exactly how a weak acid drug, like say aspirin, will dissolve and be absorbed in the highly acidic environment of your stomach versus the more neutral environment of your intestines.
And it's amazing because these principles go far beyond just digestion. Dissociation principles are used all across pharmacology to assess how tightly a drug binds to its target receptors in the body. They're used in biomolecular engineering to figure out how enzymes interact with substrates, allowing scientists to design much more effective, targeted therapies that bind precisely where they're supposed to.
Which brings us full circle. As our source material firmly points out, studying these physical properties is an absolute prerequisite. The refractive index, optical rotation, dielectric constants, and dissociation behaviors, these are the invisible parameters of safety. And the brilliant, non-destructive instruments, like our hero, the Abbey refractometer, prove that sometimes just one well-designed piece of equipment is all you really need to ensure clear liquid is a lifesaver and not a hazard.
So we'll leave you with this. The next time you take a clear, liquid medicine, whether it's an over-the-counter cough syrup or a prescribed vial, ask yourself, how many unseen tests of bending light, twisting polarity, and electrical capacitance did that tiny drop have to pass just to guarantee it would keep you safe? It's a fantastic, invisible world protecting our health every single day. Thanks for joining us for this explainer, and keep questioning the science around you.